Hello, ladies and gentlemen. Good morning, good afternoon, or good evening, depending on your time zone. I'm Pauli, faculty member and director of the Physics Institute at Campinas State University in Brazil, and also co-chair of the SCES 2020 conference. As you know, SCES 2020 was postponed due to COVID-19 pandemic, and the SCES webinar series is organized to keep your community connected and live during the absence of the in-person SCES conference. So I'd like to welcome all of you to today's SCES webinar. Thank you very much for joining us for this event, and I hope you and your family are well and healthy during this difficult time. The participants in this SCES meeting are welcome to ask questions after the talk. The participants in the Zoom meeting can ask questions using the raise hand feature, which can be found by clicking on participants or in the reactions options, depending on the version of the Zoom. In the bottom at the menu at the bottom of their screen, then clicking on the small blue hand at the bottom of the participants list box. While participants in the Facebook can use the chat to ask questions. During the presentation, please keep your microphone muted and your videos off, but you are welcome to start your videos and unmute your microphones to ask the questions. So to introduce our speaker of today, I would like to invite Dr. Stefan Wirtz from the Max Planck Institute in Dresden, Germany. Dr. Wirtz is a very active member of the SCES community and a member of the International Advisory Committee for the SCES 2020. Stefan, thank you very much for being with us today, and please, you may begin the introductions.
Okay, thank you very much, Pascal. My name is Stefan Wirth from the Max Planck Institute for Chemical Physics of Solids in Dresden, Germany. And it's my great pleasure to introduce today's speaker, Dr. Andrea Severing. Andrea studied physics at the University of Cologne, and then she went for her PhD to Los Alamos and Grenoble. And after her graduation in 1987, she continued to work with neutrons and became a beamline scientist at the ILL in Grenoble in France. She then took an extended maternity leave and eventually she returned to science thanks to a re-entry grant from the University of Cologne. And at that time, she moved away from neutrons and instead started to work with X-rays. So X-ray spectroscopy, resonant and non-resonant, inelastic X-ray scattering and so on, in an effort to actually investigate the properties of heavy fermions. And here specifically the crystal field aspects, the study of which by X-rays was new at the time in the field of F-electron physics. She's still based at the University of Cologne and enjoys a close collaboration with our Max Planck Institute in Dresden. So today, Andrea will talk about a comparative X-ray study of uranium metal to silicon compounds with 5F electron duality. So please, Andrea, we look forward to your talk.
Yes, so I start sharing and I stopped the sharing, sorry. Okay, you can see my screen, I hope.
Yes, we can.
Okay, thank you.
Yeah, that's okay.
Then yes, first of all, thank you, Pascal, for asking me to present our work here at this webinar, which I think is a great idea to have these webinars regularly. And thank you, Stefan, for the introduction. Yeah, today I will present our X-ray work, a comparative study on uranium-2Si2 compounds. And at the end of the talk, you will see that we actually nicely see the dual character of the 5F electrons in these materials, in these compounds. This is an ongoing project. It's a joint project of University of Cologne and the Max Planck Institute in Dresden. In Cologne, I'm funded by this grant from the DFG, which just got extended, so I'm very happy about this. And here are the names of the main players from the Max Planck Institute and also University of Cologne. But of course, I really gratefully acknowledge all the contributions and work from all the sample makers and sample making groups, because without them, we couldn't do this type of research. Then I would like to acknowledge the beamline scientists at Petra 3, DESI in Hamburg, and also ESRF in Grenoble. And if I show simulations, they were performed with a full multi-plate code Quanti by Maurits Havercourt, who is now based at the University in Heidelberg. This topic is of course related to the hidden order problem in uranium ruthenium to silicon-2, which is an intermetallic heavy Fermi uranium compound that exhibits two transitions, one here at 17 Kelvin and another one at 1.5 Kelvin into a hidden order, into a superconducting state. I'm showing you here the specific heat versus temperature. And it is this transition here that is still the mystery and the unsolved problem. It goes along with the formation of tiny antiferromagnetic moments. Actually, they're extremely small, 0.03 Bohr magneton, and that is too small to account for the loss of entropy here at this transition. So that this antiferromagnetic phase has been attributed to a parasitic phase. This order must be some type of electronic order that goes along with the change of Fermi surface, and there is still a debate. What is the type of the order parameter? There are many suggestions, but this is a discussion I will not enter here. Instead, I refer to review articles. The last one, the most recent one, came out actually last year, 2020. Here is, I show you the resistivity versus temperature. It is very anisotropic. Here you see the kink, that is the hidden order. This drop here may be attributed to sort of entering a coherent state. Here I show you the static susceptibility. It is also very anisotropic, showing us that their crystal field effects are actually very important in this material. I just flashed some energy scales. There is a hybridization gap has been observed in STM. It opens at low temperatures. It's of the order of 13 millivolt. You have a hidden order gap being observed in, I think, HAXPES and also in neutrons. And we have a spin resonance in this gap of 1.6 millivolt that's been observed in Raman as well as in neutron scattering. So much about this. And now I want to come to our study and work. We thought that we should maybe compare materials that are isostructural to uranium ruthenium to silicon-2, the hidden order compound, but that have very different ground states. And for this, we have chosen the ion compound, uranium ion to silicon-2, which is isoelectronic to here to the 4D of the ruthenium. And this ion compound is a Pauli Paramagnet, so it does not order at all down to the lowest temperature. And then we picked the nickel and the palladium compound. Again, they're both isoelectronic, 3D and a 4D, and they're both antiferromagnets with very high ordering temperatures and very large ordered magnetic moments. All four compounds have in common the same crystallographic structure, and if they order, they also have the same magnetic structure. That is, we're having ferromagnetic planes that are coupled antiferromagnetically along the C direction. So you may wonder, okay, there are all the similarities, but the ground state properties are very different. So that could be, for example, because the ground state symmetries are different, because different symmetries couple differently to the conduction bands. But I can tell you already, it's not the case here. All four compounds have the same ground state symmetries, so that we have to look further. And we have to look at the degree of itineracy. In the past, over the last years, there has been a lot of work being done on uranium ruthenium to silicon-2. Attempts with state-of-the-art spectroscopies to determine the filling of the 5F shell. It seems to be confusing, but anyway, I mean, we figured it's maybe a better idea simply to look at the trend within this family. And for this, we think that photoemission may be eligible, but certainly photoemission is probably the best technique in order to see hybridization effects. But first of all, now I want to talk about the ground state symmetry and show you what we found out there. We investigate this with a method we call NIXS, and NIXS stands for non-resonant inelastic X-ray scattering. We performed this experiment at the uranium 045 edge, that is the transition from the 5D to the 5F. So we're really probing the 5F shell. I will spend a few minutes on this technique because I think it is not as well known or established as X-ray absorption or photo emission. So just be a bit patient. So NIXS, what is NIXS? It's a photon in, photon out technique. We come in with 10 kV with hard X-rays. We have a certain momentum and energy transfer. We're using the energy transfer for this core hole excitation, for this transition 5D to 5F. The nice thing is that being non-resonant is that the modeling is much easier than in a resonant experiment. 10 kV also means that we are truly bulk sensitive. We don't need UHV, so we could have fancy sample environment like pressure cells, but for us, the most important thing is that we can reach large momentum transfers if we go to backscattering geometry. Yeah, we can reach momentum transfers of the order of 10 reciprocal angstroms, and this is important for us because this brings us into a scattering regime where we can access beyond dipole scattering. And why this is important for us, I show you here on the next slides. This is the dynamical structure factor that is used or applies to this non-resonant scattering. We go from an initial into a final state via this transition operator that you may expand into QR, Q being the momentum transfer. And if we now have really large momentum transfers, as I said, we can reach this about 10 reciprocal angstroms, then we no longer can truncate it here after the first terms. We really have to take higher terms along. And these are these so-called higher multipole terms or beyond dipole terms. So they give new contributions to the scattering more than just dipole scattering. You may then expand your dynamical structure factor in spherical harmonics and factorize it into a radial part and into an angular dependent part. Important is that we don't have an infinite number of orders here. This number of K is actually limited, and this is limited by what is called the triangular condition and the parity rules. That means for the transition we are looking at for the uranium 045 edge, this D to F transition, that we go from L equal 2 to L equal 3, we only have the dipole, the octopole, and the tria contra dipole, or what it is called. So we only have 3 contributions. And here I'm showing you these 3 contributions. I'm showing you the radial part versus momentum transfer. And you see that for low momentum transfers, the dipole is the most important one, which is of course not very surprising. But at here, about 10 reciprocal angstroms, we have the octopole and the tria contra dipole are most important. They actually are more important than the dipole. And if you now look at the angular dependent part here, at this part, versus energy transfer, we see that the octopole and the tria contra dipole actually give rise to extra excitations. This has indeed been observed in a real experiment. I'm showing you here a NIXS experiment of polycrystalline uranium dioxide from Roberto Tracufo. Its intensity versus energy loss. And here for low momentum transfers, you see this very broad, almost funnel-like type line shape. It actually looks very much like an X-ray absorption spectrum. And indeed, for low momentum transfers, the NIXS, the non-resonant scattering, is very much like an X-ray absorption experiment. Whereas if you go to high momentum transfers, as here, you have these extra intensities coming up. So this experiment really shows that indeed for large momentum transfers, we do have higher multipole transitions in our spectrum. If you now do such an experiment on a single crystal, where we look at the directional dependence of the momentum of the scattering intensity from the direction of the momentum transfer. So like in a tetragonal system, we look momentum transfers along the tetragonal axis or in the plane along the A-axis. Then we can have access to the orbital anisotropy via multiple selection rules. This is very similar in analogy actually to X-ray absorption, where we have the linear dichroism and where the dipole selection rules give us access to the ground state symmetry. We simply exchange here the direction of the momentum transfer with the electric field vector in X-ray absorption. There are several advantages or additional things you may learn from a beyond dipole NIXS experiment over IXAS, But for us, the most important aspect is this here, and this is that these multiple excitations are more excitonic. Here you can see that here, this is the dipole, very broad, and these are more excitonic, so we do not have to work with energy-dependent line broadenings and difficult things like that. Plus, they really give us a nice contrast in the signal. We can model this quantitatively by using this full multiplet code. We get the atomic parameters from the Cohen code. Of course, as a fitting parameter, we have reduction factors for the later integrals, which we need to account for the configuration interaction that is not here included in the Hartree-Fock calculations, and in order to account for covalency effects that are not in the ionic crystal field calculations. And this now brings me to our first experiment that was performed at the time on ID20 at ESRF in Grenoble. This is the experiment on uranium ruthenium to silicon 2 with this large momentum transfer, and you see here intensity versus energy transfer. We have here the elastic scattering, and we have this huge Compton scattering. Yeah, and on top of this, you see these spikes. Here, this has been measured with a very coarse step width, and these are the absorption lines. And here we have the uranium 045 edge, and what we do is we're sitting in this energy range, and then we are scanning with a smaller step width, and we're really counting, we're really collecting statistics. So we have error bars like in a neutron scattering experiment, statistical error bars, yeah. So this is this experiment here on uranium ruthenium to silicon 2 for the two directions, parallel, momentum transfer parallel to the C direction and parallel to the A direction in the plane. And we have a huge anisotropy. But just looking at this data, of course, we cannot say what is our ground state symmetry. In order to do so, we have to simulate, we have to model these data with our full multiplet calculation. But first of all, we have to actually find a description for the overall line shape before we actually try to model the directional dependence. And this we do by simply constructing isotropic spectrum by simply adding up the different directions we have measured. We make an isotropic spectrum, or here, because it's beyond dipole, we call it pseudo-isotropic because we need more directions. And that we then try to model with our full multiplet calculation. We do the modeling for the uranium F2 configuration, atomic values from the cone. We have the spin-Overton Coulomb interaction for the J equal 4. And then we're fitting the reduction factors for the, yes, we're fitting the reduction factors here for the later integrals of the Coulomb interaction 5F, 5F, and 5D, 5F. And we find that we have to reduce to 50%. This is necessary in order to get here the energy distribution of the multiplets. Yeah, if you have a strongly hybridized system, it usually, the energy distribution shrinks, and that you can capture by having a strong reduction. This then tells us that we are sort of in the intermediate, or brings it to the intermediate coupling regime, where we find this ratio of the orbital momenta. So we have mainly the L equal 5, but we also have 4 and 3 contributions. As a given, we have the resolution function. Another thing we can fit is the line shape, so we can fit some lifetime broadening, and we have some asymmetry, which might be another fingerprint of hybridization effects being present here in this system. And what we're ending up is this simulation. We think that the agreement actually is pretty good. So we are quite happy with this F2 simulation. But just for comparison, I would like to show you what an F3 would look like. Here I show you the data of uranium cadmium 11, which is sort of an intermetallic F3 type compound. It has a very different line shape, yeah, and there is a certain energy shift. And we can simulate this actually rather nicely, again, with such a full multiplet simulation, but this time assuming an F3. Okay, so we are happy starting with an F2 configuration. This is now the simulation based on this, what I just showed you for the isotropic spectrum. And on top of that, we are now taking into account the point symmetry of a D4H symmetry of uranium here with a J equal 4. And that's what we find for the 7 crystal field states of uranium in this UM2 silicon 2 structure. These are these 7 crystal field states. Here we have the 2 doublets, yeah, these are the gamma 5. We have the 5 singlets, and these are here the 5 singlets, gamma 1, 2, 3, and 4. If you now compare that with our spectrum, directional dependent spectrum, well, I think we have red over blue. We have red over blue here, but blue over red we can discard right from the beginning, so we don't even need to consider these further. So these here, the gamma 2, gamma 3, gamma 4, and also this gamma 5 at the bottom are out right from the start. But what is left are these two, and here also this gamma 5 on the JZ3 plus minus 3 side has a red over blue anisotropy. So to be more quantitative now, we look at the difference plot, which I show you now in black. Here I show the same difference plot 3 times. These are the black points. And this is overlaid with a simulation. Yeah, the difference of this gamma 2 here, that is here the green line. And this is the difference plot for the gamma 1, 1. Not only for 90 degrees, we are allowing a little bit of JZ plus minus 4, so we say 70 degrees to 110 degrees would give a good match here with the data. If you now look at the gamma 5, the biggest dichroism we get is far away from what we actually measure. So that really on quantitative grounds, we have to discard the gamma 5 as an option for the ground state symmetry. Our conclusion is that only the gamma 1, 1, very much on the JZ plus minus 4 side, or the gamma 2 actually are able to describe our data. And this is something we published already 2016 here in this journal. It's interesting to note that here in this nice publication, that we have actually a very good agreement with DFT plus DMFT calculations. They also find that most occupied is the n equal 2 configuration, and especially these gamma 2 and the gamma 1, 1, these are here these states, are the most occupied states. So with this now, I come to our directional dependence study. I will now show you the same type of data for the palladium, the nickel, and the iron compound. These experiments were performed at DESY in Hamburg at the Max Planck beamline PR1. Again, we come in with 10 keV incident energy. We have about the same resolution and the same large momentum transfer. These are the data from ID20 you have seen before, at the bottom the difference plot. And these are now the data of uranium palladium to silicon 2 and uranium nickel to silicon 2. I think if you look and you compare it with the uranium ruthenium to silicon 2, you have to admit the spectra look pretty much the same. Yeah, it is here red over blue, blue over red, the same here, and the same is for the nickel. The only difference is here, but this is because here we have the nickel M1 edge, a strongly dipole forbidden line, but because we're in the beyond dipole limit, it actually has quite a bit of intensity. So we now come to the iron compound, the Pauli Paramagnet, and also this exhibits clear multiplets. We have a big difference here, but this is because the M1 edge, which appears in nickel here, appears for the iron here in energy, so it is distorting this part of the uranium 045 edge quite a bit. But if you look at this part of the spectrum, it looks again very much like in the other compounds. Here at the bottom, I'm showing you difference plots. And there, I think I didn't say that the full, so all these data here are taken at low temperatures, so something like around 10 Kelvin. And the open dots here now on top of the full circles were taken at 300 Kelvin. So this is just to show that we actually have no, I would say no temperature dependence in our data. So we are not starting to fill excited crystal field states here. So we are summarizing this, or what we are learning from this is that all 4 compounds have the same ground state symmetry, the gamma 1 singlet on the JZ plus minus 4 side, the gamma 2 singlet, or what we cannot distinguish is, of course, in case both sides are very close in energy. So how I could convince you now that the symmetry of the states is the same, so this is not the reason for the different ground state properties, so that we now move on and we look at the itineracy of our materials. And at the itineracy, we look with core level HAXPES. HAXPES is in principle the same as photo emission, but with hard X-rays. So we come in here with 6 keV. That is, we have a larger probing depth than in photo emission. This experiment was also performed in Hamburg at the beamline P09 that then later moved to P22. Of course, if you do photo emission, even when you do photo emission with hard X-rays, you have to cleave, which is a complication because cleaving uranium, not everybody likes. So we have to make some efforts bringing our own cleaving chamber here from Dresden to Hamburg, attach it, and dismantle it after the experiment. But by now we have a nice routine with radio protection actually at DESY, so it works out rather nicely. And these are the first spectra I show you. These are HAXPES data of uranium-cadmium-11 in blue, recall. This is the F3 type compound. And I'm showing you here the uranium 5F emission lines, and what you see here is the cadmium emission, so that is something you just forget about this. And in addition, I show you the uranium palladium 3, which is sort of an F2 type uranium compound. Actually, I think to my knowledge, the intermetallic that is most on the F2 side, or known to be most on the F2 side. After subtracting a background, integrated type background, the spectra have been normalized to the integrated intensity here in the region of the uranium 4F emission lines, something which is justified because the 4F shell is an inner shell and all the compounds have a 4F shell, so there are 14 electrons in the shell. What you see is actually quite a big difference. The F3 type compound has a very high intensity here, whereas the F2 has really shifted in energy and has a lot of intensity here. Yeah, I'm now overlaying here the gray shaded areas, the uranium, ruthenium to silicon to HAXPES data, also taken at low temperatures. And first of all, I should remark that actually our data agree quite nicely with photo emission data of Senji Fujimori, who published this in 2012. Yeah. But from this way of plotting the data, I think one can see nicely that the uranium ruthenium to silicon really has aspects of both, of the F3 type compound, but also of the F2 type compound. So that our conclusion is uranium ruthenium to silicon is strongly intermediate valent. And now I come to the comparison. Yeah, I'm showing you the same uranium ruthenium to silicon spectrum again. Is only on a different Y scale. I've expanded that here. And we now compare it with the ion compound, with the Pauli Paramagnet. And you see there is a shift of spectral weight. We're having more here and we have less here. So if you compare that now with our reference compounds, we're having more here and less here. So that we can say, well, going from ruthenium, from the hidden order to the Pauli Paramagnet, we are having a shift towards the F3 spectral weight. We have more F3. We now come to the antiferromagnet, to the nickel compound. Well, then it drops, but we have more here. Again, if you compare, we have to say, well, going from ruthenium to nickel to the antiferromagnet, we have less F3 and we have more F2. And we go to the palladium and it drops even further and we have even more F2. So what you learned from this is that, well, all uranium M to silicon 2 compounds are intermediate valent. And we have a successive shift of spectral weight from F3 to F2 in this sequence. Yeah, we go from the Pauli Paramagnet via the hidden order to the antiferromagnetic compounds. And our interpretation is that this is a sign for a decrease of FD hybridization in this sequence. And that is justified when we look at an FPLO calculation for the density of states, which I'm showing you here, again for the iron, ruthenium, nickel, and palladium compound. I'm showing you in red the density of states of the 5F, and in color, the same color coding as here, the D states. And what we can say is the more the D states overlap with the 5F, broadening the 5F as well, the more of the F3 we see in the HAXPES data. When you go from the iron to the ruthenium, the D states are moving away. Well, here we see the drop. You go to the nickel, it drops even further. and we're looking at the palladium where the D states and the 5F states are furthest apart, we really have the smallest F3 intensity and the most of the F2. And this already brings me sort of not to the end of my talk, but to a certain summary, or to a summary of our experimental data. I think I've shown you that all 4 compounds actually show multiplets of the uranium F2 configuration, and that they all have the same symmetry, excuse me, namely a singlet gamma 1 or a singlet gamma 2. At the same time, I'm telling you, all 4 compounds are intermediate valent, and that we're having this successive shift of spectral weight that we explain with a decrease of FD hybridization in the same order. I would like to point out that seeing F2 multiplets here in all 4 compounds, but telling you they're all intermediate valent here is not a contradiction. It is not a contradiction because this is something Gunnarsson and Schönhammer and also Frank de Groot have shown a long time ago, that if you do an X-ray absorption experiment, and NIXS is very much like an X-ray absorption experiment, and you look at a D to F transition in an F electron material like the rare earth or the actinides, or you look at a P to D transition in a 3D material, then X-ray absorption or NIXS highlights actually the configuration that is lowest in energy. And this clearly here is the F2 configuration for all 4 compounds. Yeah. HAXPES, or photo emission, on the other hand, is more sensitive to hybridization and sees more the non-local effects. So we're having 2 different spectroscopies that highlight 2 different aspects. Seeing the local aspect here, seeing the non-local hybridization aspects here, brings us, I think that is a nice concept here, this dual nature ansatz for 5F electrons, which means that 2F electrons are considered to be localized, and the third one should or is responsible for the heavy fermion properties, something that has been applied here to other heavy fermion compounds. The most recent one I found was on uranium platinum to silicon 2. If I were you now, I would be wondering, I mean, that's all very nice, why I'm telling you, or I'm trying to sell you, that we are having singlet ground states, although we have 2 compounds, the nickel and the palladium, that are antiferromagnets with high ordering temperatures and really large ordered moments. Because indeed, all the singlet, I'm showing you here the crystal field states again, all the singlet states don't carry any moment, only the doublets do. At the same time, these large ordered moments have been observed in the nickel and the palladium compound. This you can accommodate if you accept that we are dealing here with some induced type of magnetic order, where 2 singlet states couple because the energy splitting is smaller than some exchange interaction that couples them. And if we accept that, and these 2 states couple, by symmetry they're allowed to couple, to a quasi-doublet, we may have any moment between 0 and 4 Bohr magneton, which would accommodate nicely this large ordered magnetic moments that have been observed. You could also have a quasi-doublet consisting of these 2 states, but there you cannot reach such big moments. So I think this is sort of, for us, a nice confirmation of our experimental findings. And now I'd like to take a step further, and I'm showing you here the Gunnarsson and Schönhammer ansatz for the total energy diagram of these compounds. I already told you that the F2, or I call it here F2 ligand electron, is lowest in energy, and we're having here our quasi-doublet consisting of the gamma 1 and gamma 2 singlet states, and that is hybridized with an F3 Kramer's doublet. Yeah, and that this hybridization then pushes out a mixed Kondo state that, in the case we know for uranium ruthenium to silicon 2, I mean, there are these STM measurements giving the hybridization gap is of the order of 13 millivolt. Having done that, we can go even further and say, well, now we may as well use the systematics and have an effective Donner phase diagram for an F2 manifold, where we're plotting the temperature against the exchange interaction being given by V square, V being the hybridization divided by epsilon sub F, here being this energy difference. There, of course, we put the uranium ion to silicon to sample the Pauli Paramagnet here in the Fermi liquid regime, the ruthenium, which does not order magnetically, here close to the quantum critical point. I mean, you may recall it's also the only compound that exhibits superconductivity, plus you can easily push it with pressure into the antiferromagnetic regime. And the nickel and the palladium compound are well in the antiferromagnetic regime. And with this, I come to the end. I have now added here to my summary that induced type of order having a quasi-duality system made up from these two states can account for the large moment. And it also may provide the degeneracy that you need to build up your hidden order state. Like I think there has been this proposal of a static order where you do need sort of a doublet, at least you need a higher degeneracy so that you can account for the loss in entropy. And with this, I would like to thank you for your attention.
Thank you very much, Andrea, for this nice talk. Maybe I can ask all the participants to unmute and give Andrea a hand, and just to show it really was a nice talk. And thank you very much. And now I would like to ask for questions. If there are any questions, please use the raise hand tool. And then I hope I can see that on my screen. So far, I don't see any.
So my name is Fouquet. I can ask a question.
Hi, Jacques.
Of course, go ahead, Jacques.
So just my remark is that it is well known that you can get intermediate valence, and then anyway, when you normalize, you normalize to one given representation. It means 5F2 and 5F3. I think what is nice is that you show more seriously by microscopic measurement, but I think it is, at least for me, it seems to be known. But of course, this cannot be proved microscopically, and you prove it, so it is fine. If you want to compare uranium compound with fluctuation between two magnetic configurations, the more near case is the case of thulium. When you go from thulium telluride, thulium sulfide, thulium selenide, thulium sulfide, you have exactly this game. So you try to think to repeat experiment now on thulium compound, escape from uranium and go to thulium.
Yeah. We have not been thinking about thulium. I have to say, indeed, I mean, it has always been discussed that there is a valence between 2 and 3 in these compounds, but I think what is new and what is an important finding is that the symmetry of the ground state is the same, because I think you can only compare this or put this into in a trend and into some systematics if you know that they all share the same ground state symmetry. And this is here a crucial point. But we have not looked into thulium, but it's a good idea. Maybe we should do that.
Okay.
Thank you.
Nice. Okay. Thank you.
Could I maybe stop the screen sharing or go out of presentation mode? Could do that maybe. Yeah.
Well, I don't see any raised hands here.
I have a question.
Go
I'm
ahead.
sorry, I could not find where to raise the hand.
Okay.
Is it okay, Stefan?
Yeah, go ahead.
Yeah, very beautiful results, Andrea. Yeah, very interesting that you proposed a dual nature here, and it looks consistent with measurements. But as you said, the X-ray spectroscopy, it will always give you a more localized picture. Yeah. So I was wondering if one goes to the photo emission spectra that you also have in your PNAS paper, and you compare that to DFT, yeah, for the compounds. Well, it is in your PNAS paper, the valence band.
Yes, we have that. Yes.
Maybe
You want me
you
to
don't
show
have
the valence?
So my point is, if you would say there is the localized 5F2 contribution, but it is not seen in the valence band photoemission spectrum. Yeah, they look all very fine if you compare them with the FPLO calculations.
Yeah, this is true. I think I have this actually here. I only have to.
Yeah,
this is what you mean, no?
Yeah, that is what I mean. So if you go to uranium, ruthenium 2 on the left, I see no discrepancy. Yeah, if I put a 5F2, I would shift the spectral weight away. Yeah, so how do I see it here? That is my point.
Well, of course, what we did is we have been integrating and we have tried to get the filling of the 5F shell out of this. But I don't know how reliable this is. So we all find when we do sort of, we integrate here and we all find that all compounds are strongly in the intermediate valent regime. So we get an F shell filling of 2.5 roughly.
Okay, but if I would have a 5F2 localized contribution, I would expect a bigger shift of the weight to higher binding energies. Yeah, but I don't see it. It might be that it is there, but
yeah, I agree. I don't see that. Yeah.
Okay.
Yeah. Okay, thank you. To think about that.
I see Anna with a question. Anna, go ahead.
Thank you.
Hi, Anna.
Hi, it was a very nice presentation. I think it was very clear, so thank you very much. So you take special care when you compare all your compounds that they have the same crystal symmetry, but when you make this comparison with HAXPES, that you compare with uranium cadmium 11 and uranium palladium 3, but these have different crystal structures. One is cubic and one is hexagonal and the other ones are tetragonals. So is that any effect? So is it
I think yes. I think
different crystal structures.
I think yes. This is why we cannot do any quantitative analysis here. Yeah, that's why we only say, well, this is here F3, and we go more to this energy range here, and it is becoming F2. Also, if you look really in detail, you see that this peak here is slightly shifted in energy in comparison to this one. Yeah, so I think if you look at really different compounds, you should take the comparison with a pinch of salt. In order to really look at the systematics, I think you have to make sure two things. They share the same symmetry, that you can be sure the same symmetry couples to the conduction band. And second of all, yeah, I mean, then they will have the same symmetry anyway, crystal symmetry, yeah. Yeah.
And other compounds than in the 1 to 2 structure, which are completely localized, can you find one?
Well, it's an ongoing project. We are sort of looking at more compounds, but that is really work in progress, yes.
Okay.
There are surprises in the 5Ds, I think, yes.
Yeah. Thank you for the answer.
Thank you, Anna. Yeah, I see another question by Krish Bloomberg. Please go ahead. Unmute yourself.
Yes, very nice talk. Thank you. Hello. What I just want to emphasize that again. I'd say that entirely consistently with what you say. Low energy spectroscopy observes this pseudo doublet directly. So this excitation of 1.6 MeV is actually those two states, gamma 1 and gamma 2, and then the magnetism follows exactly as you say. So it's another direct way to see that. Well, that's so this is entirely consistent with what you're saying.
Okay, thank you. Andrea, can I ask a question actually? When you showed your result on the uranium ruthenium 2 silicon 2, you had these different states, and you had right from the beginning taken some of them off with the argument that one was blue over red, the other one was red over blue. But in the end, you did a fitting. And my question is, can you really throw that away right from the beginning? Because you could have a case in which is really blue over red, but with a smaller contribution that's eaten up by something which has a much larger contribution with red over blue. I understand that it would be a minor correction. I mean, there is a sum rule here, yeah. It must be a minor correction, but to throw it away straight from the beginning, I find a bit, well. Do you have any? Can you comment on that?
Yeah, I mean, you mean that we have a state in principle that does not have any dichroism. Of course, that would be invisible. Yes.
Yep.
Yeah.
Okay.
But what we, if they all were low-lying states. I mean, what we did, we measured here at 25 Kelvin, right? We even went down to 5 Kelvin. And then I don't have the data here, but we have this in this 2016 publication. We measured successively up to 300 Kelvin in smaller temperature steps. And we don't see any changes. So we are not depopulating or populating anything. So it really, it seems, yeah.
Yeah.
We have two identical states close by an energy at low T.
No, my remark won't change any of your conclusions for sure. Okay, I can't see any further question. Maria, do you have anything on the chat?
No, we have nothing.
Okay, so
can I maybe also ask a short question, just without raising a hand?
Oh, that sounds like Daniel. Yeah, go ahead.
If you have a ground state which is very close singlets gamma 1 and gamma 2, if I consider it as a kind of non-Kramer's doublet, simply speaking, then complex combination would give you a magnetic state, but real combination gamma 1 and gamma 2, do they correspond to particular quadrupolar distribution of charge density, and is it really consistent with the local crystal structure?
Yeah, it is. Yes, by symmetry, there is allowed that these two mix. Yes.
Yes. That's actually that's exactly what you have here now on the picture. That's actually quadrupolar distribution of charge density at gamma 1 and gamma 2. Okay, and how charge density would look if you make this complex combination? Say gamma 1 plus I gamma 2, which is magnetic. Will it be completely kind of cubic or symmetric? I mean, total charge distribution. If you plot it, gamma 1 plus I gamma 2, how would it look?
What I can say, if I mix it here the 0, of course, I do get dense in this one here. Yeah. But I have to say, I did not look at it because we're getting the magnetic moment for exchanging the JZ plus minus 4. No. I have not looked at this. I have not. We should look at this. I have not plotted it.
Because it's also rather similar to simple 3D electrons with EG levels, doubly degenerate, which I can describe by effective pseudo-spin tau 1/2, in which tau Z and tau X is quadrupolar operator, but tau Y is magnetic. But now magnetic, is it really magnetic dipole or something more tricky like magnetic octopole?
Yeah, that's the question.
Gamma 1 plus I gamma 2, is it really magnetic dipole or magnetic octopole?
I think
Daniel, if I may, we analyzed that in our paper. So it's a combination of the gamma 2 is a hexadecapole. So it's a combination of singlet with hexadecapole. And,
no, but I mean just if you make complex combination. Here.
Yes, yeah, you need to make the complex complete.
But if you make complex combination, gamma 1 plus I gamma 2, for example, I break time reversal symmetry, so that will be magnetic state, but it's not necessarily magnetic dipole. It might be something like magnetic octopole or something like that.
You are correct. It's a high order multiple. Yes.
It's not magnetic dipole.
It's
well, Gersh, I think if you look at the nickel and the palladium compound, it's a magnetic dipole, no? But not in the ruthenium.
Not in
No, but that's exactly the point, because if it's magnetic octopole, not magnetic dipole, then the question would be, what is this antiferromagnetic order? That actually very similar situation was considered for some rare earths by some people like Gang Chen and so on, like 3 plus minus 3 or whatever, something like non-Kramer's doublet, in which real combination are also quadrupolar and or maybe magnetic dipole, but complex combination is magnetic octopole. So that's my question essentially, whether you have here complex combination would correspond, any complex combination would correspond to real magnetic dipole or magnetic octopole. That's my question.
We do have that analysis in the supplementary that Andrea referred to. Daniel, you can look in that. It's a little bit. It does couple to linear magnetic field along c-axis, but it does also more. So it's more. Now there is a further. There is a.
So is the standard Zeeman effect for this one?
There will be a Zeeman effect as well. Yeah.
There will be. So there is a real magnetic dipole composition.
There is a component of that, but it's more. Yeah, but it's more than that. Yes.
Okay, very good. Okay, great. Thanks.
Okay, are there more questions? Anyone? No? So I think then we close the session, and I would like to actually thank Andrea again for this really nice talk, and maybe we can give her another round of hands. So.
Okay, thank you.
Thank you very much. Do you wanna say something, Pascal?
Yes. So thank you, Andrea, for the nice talk. Thank you, Stefan, for helping us to co-chair the section. And before we finish, I would like to kindly ask all the audience to start their videos so I can take nice pictures of this nice audience. Perfect. Thank you very much. It was very nice seeing you all, and I hope to see you again next month in the next SCES webinar. Thank you. Bye-bye. Stay well. Take care.
Bye-bye.